Okay, I'd like to take a little time here and talk about harmonics and octaves for you music physics people out there. Harmonics and octaves. Before I do that, I'd like to kind of talk about two different words here that you might have in music and kind of making sure that we understand the difference between them because sometimes people get them a little confused. So the first word is actually volume. So volume. And then the other word is pitch. Okay, you can change your pitch, you can change your volume. Volume is how loud you're singing, And if I looked at a sound wave, what characteristic of the wave would that be determined by? That would be determined by the amplitude. So if something's really tall, it has a big amplitude, it would be loud. It would have a big volume. Pitch, though, is not how loud you are. It's not how loud or soft you are. Volume is how loud or soft you are. It has to do with the amplitude, how tall the wave is. Pitch is how high or low you are singing, how high or low you are singing, and this has to do with the frequency. So if I have a note that's like this, okay, or I have a note that's like this one here has a higher note than what this one is here. This is a high frequency, so it's a high note. This is a low frequency, so it's a lower note. Okay. By the way, lower frequency means a longer wavelength, and longer wavelength means that things will diffract around things better, by the way, right? So just a little, here's how physics can save your life. It's a wilderness survival tactic that if you're lost in the woods, you should yell, "Help!" You should not yell, "Help!" like that, because, sorry, I choked there. If you yell in a high register, it's a high pitch. It has a small wavelength, and small wavelength things don't bend around and diffract around things like trees and buildings nearly as much as long wavelengths do. So you should yell help in a low register or a low frequency, which means a long wavelength. I don't know why I told you that. I thought you'd just find that really interesting, so I just threw that out. Okay, so what are harmonics? Harmonics, in music, you might have called them overtones. Okay, overtones, harmonics. This is very simple. Harmonics are just different modes of vibration or modes of oscillation that, like a string or vocal cords or air in a column, a saxophone or whatever, can vibrate at. And they're actually just whole number multiples of some fundamental frequency. Whole number multiples of some fundamental frequency. I'm going to explain that here in a little bit more with some math, but before we do that, I would like us to look at like harmonics, modes of oscillation that could happen in like a guitar string. Okay, we're going to do it a guitar string. Guitar strings will be clamped at either end. So at either end of a guitar string, we would have what we call nodes. We've talked about this a little bit before. And a wave can travel back and forth between those two nodes. So as a wave goes to one end, and it's a fixed end, it'll reflect 180 degrees out of phase and come back on itself. And then so any waves going down the string will interfere with waves coming back on the string, and we get what is called standing waves. Hopefully you already kind of understood standing waves from the last unit, how standing waves formed. And so the most fundamental way a standing wave can form is in between two nodes would look like this first thing right here, which we call the first harmonic, which I don't really like because it's not a harmonic if it's the only one, right? So generally I call this the fundamental, right? The fundamental. I like to use the word fundamental. I very rarely will call it first harmonic. I'll just say it's the fundamental, and then you have the second harmonic and the third harmonic and the fourth harmonic and so on, okay? So the fundamental mode of oscillation of a string, anything that's clamped on both ends, has nodes on both ends, would look like this. It could be up as a big crest, or then it could go down as a big trough. So it's kind of like a jump rope thing. It's just going to be one or the other is how you're going to have it there. Okay, I'm going to kind of show you a little animation here on this. the way that this would work. So here is a two fixed ends. We have a fixed end here, and we have a fixed end here on this other end. And this is actually a resultant wave. So you have a wave going down this, and it's interfering with a wave coming back. And they would interfere all the time to make this standing wave pattern. This is the most fundamental standing wave pattern you can get when you have two fixed ends. See, I have it on two fixed ends. You could have one open end. You could have two open ends. Those are your other options. We are going to come back and visit this later when we talk about standing waves in like tubes or musical instruments. But this is the standing wave you'd get on a guitar or like a piano string. You'd have fixed ends on the end, and this is the way we can do it. So I'm going to just be in this mode right here. By the way, I can click on like a blue wave and an orange wave. These are the actual waves going down the string and then coming back and bouncing. You know, it's every time you have like one up here, it's going to be 180 degrees bouncing back. But so they're going to interfere with each other, so you won't see any of those individual waves. You just see the resultant of those two waves interfering to make this green standing wave. So I like to hide those so you don't get confused by them. But those are actually what's in there. So this is a standing wave you can get. Okay. Now, what would the wavelength be? What would the wavelength be of this standing wave? Well, a wavelength is a crest and a trough, right? So in between this point here and this point over here, by the way, I've already counted out, there's 24 boxes. We'll call each box a meter. So we'll say that right from here to here would be 24 meters long. Is that a wavelength? No, it's not, because what you have in between these 2 points is like a crest right there, or a trough. That's all you have. So right here from this point to this point is actually half of a wavelength. And that's 24 meters. So a full wavelength here would actually be twice the length from here to here. Okay, we'll call the length from here to here L, right? We know it's 24, but we'll call it L. So what's a wavelength for the fundamental mode of oscillation? It would actually be 2L. 2 times this length would be your wavelength. The wavelength here, if this is 24 meters from here to here, the wavelength is actually 48 meters. Okay? All right. So what I want to do is I want to go to the next harmonic. I want to take whatever frequency this is. By the way, what is the frequency? Oh, yeah, so it tells us the frequency, 0.067. I want to double that frequency, which means I want to go to the next harmonic. 2 times that frequency is the second harmonic, and see what happens to wavelength. So if I do that, if I click next harmonic, now I get a different standing wave pattern. This is the other standing wave pattern that can form on a guitar string. And you'll notice we have a kind of a loop here, we have a loop here, but now we have a node in the middle. Okay? We have maximum displacements, and we have a node in the middle. What is the wavelength? Well, now I have a crest and a trough. When this is a crest, this is a trough. And so I have a full wave in between here. So from here to here is a wavelength, and it's actually 24. So I doubled the frequency. Notice I doubled the frequency. And that cut the wavelength in half. Instead of 48 meters, now it's only 24 meters. But this is the second standing wavelength I could get, and that's called the second harmonic, right? If I go back to the first harmonic, the fundamental, you just have one loop, right? There's just one loop. If I go to the second harmonic, you have 2 loops, okay? The number of loops will be the harmonic number, right? Okay. So now I click the next harmonic, and this is the next standing wave pattern I can get if I have 2 fixed ends. And you'll see it's the third harmonic because there's 3 loops. 1, 2, 3. 3 loops, okay? How long is a wavelength now? Well, a wavelength is actually always 2 loops, right? A crest and a trough. So it'd be from here to this node right here. How far is that from here to here? That's 2/3 of the length, right? 2/3 of the length. Okay? What's 2/3 of all the way out here to 24? Well, you'd have 1/3 would be 8, and another third would be 16. So the wavelength for this wave is 16 meters. I can do the next harmonic. Now I have 4 loops, right? And 1 node, 2 nodes, 3 nodes, things that aren't even moving at all, okay? So this is the 4th harmonic, and the wavelength would actually be 2 loops. It's always 2 loops, so crest and a trough right here. instead of 24 meters, it'd actually be half the length. It'd be 12 meters would be my wavelength now. Okay? I get the 5th harmonic. I get the 6th harmonic. I don't know how far I can go. 7th harmonic. Did it do that? Or 8th harmonic? I guess it is doing it. It's just really, it's going to be super high. It's going to be, let's click it all up way up here. I can't do it anymore. Okay. All right. Go back down. There's the 3rd harmonic right there. And the wavelength would actually be 2/3 the length between these things. Okay? It's the 3rd harmonic, so it's 3 times the fundamental frequency. 3 times the fundamental frequency. Okay. Maybe that helped you a little bit with harmonics. We want to also talk about something called octaves. So I'm going to draw a little bit here on a piece of paper. Okay, and so I'm going to say harmonic. Okay, and I'm going to do 1st, 2nd, 3rd harmonic, 4th harmonic, 5th harmonic, 6th harmonic, 7th harmonic, 8th harmonic. I'm going to do it like this. Okay, so I'm going to do some frequency. I'm going to pick a frequency. Okay, and let's say that the frequency is. I'll make the math easy. The frequency is 100 hertz. 100 hertz. Okay, I have a 100 hertz note. You'd be able to hear that because it's in between your 20 and 20,000. 100 hertz note. All right. So this is easy for a Jedi trial. If I say I have a fundamental note of 100 hertz, what is the 2nd harmonic? Okay. So this 100 hertz note is going to be what I call the fundamental, right? The fundamental, or what some people might call the 1st harmonic. Okay, the fundamental note is the 1st harmonic. What is the 2nd harmonic? Well, harmonics are just whole number multiples of the fundamental. So the 2nd harmonic is actually a note of 200 hertz. It's that easy. What's the 3rd harmonic, or the 3rd overtone? It would be 300 hertz. What's the 4th harmonic? It'd be 400 hertz. So you're just taking the harmonic number times whatever your fundamental was. The 4th harmonic of a 100 hertz note is 400 hertz. 500 hertz, 600 hertz is the 6th harmonic, 700 hertz is the 7th, and 800 hertz would be the 8th harmonic. Okay, so harmonics are a piece of cake. Take the harmonic number times the fundamental, and you'll have the note that you're going to be on. Okay, but what about octaves? Octaves. Some of you in music have heard of octaves. The reason it has oct on there is there's 8 notes on a scale. 8 notes on a scale. You could go from a C, and then you could go to a D, and then an E, and then an F, and then a G, and then it starts over A, B, and you could go to a C. That's 8 notes, 8 steps there between one note and a note that's an octave above. Okay. So, how do we get octaves? Octaves are if you sing a note of 100 hertz and then you go up 1 octave, what note would you be singing? Okay, you'd actually be singing a note of 200 hertz. So whenever you go up 1 octave, this is the key. Whenever you go up an octave, you double the frequency. Whenever you go up 1 octave, you double the frequency. So if I have a 100 hertz note and I go up 1 octave, I'm going to have a 200 hertz note. So right here is the 1st octave. That's 1 octave above the fundamental. Okay? I'm doubling 100 hertz, I get 200 hertz. So the 1st octave is actually also the 2nd harmonic. The 2nd harmonic is the 1st octave. Now what if I go up another octave? Well, now I'm going to double this note, right? So I sang a 100 hertz note, I went up 1 octave, do, re, mi, fa, sol, la, ti, do, all the way up. Okay, then you'd be at 200 hertz, right? And if I double that again, okay, I'm going to be at 400 hertz. This is the 2nd octave. This would be the 2nd octave up. I'd be at 400 hertz, which you'll notice, by the way, is the 4th harmonic. The The fourth harmonic is the second octave. The second harmonic is the first octave. What if I go up a third octave? I'm going to now double the 400. Now I'm here, 800. So I'd have a third octave. A third octave is the 800 hertz, which would be the eighth harmonic. Okay, the eighth harmonic. Okay, so the second harmonic is the first octave, the fourth harmonic is the second octave, and the eighth harmonic is the third octave. So an interesting pattern, if you just keep doing this, I don't know, can you figure out what the fourth harmonic would be? The fourth harmonic, the fourth octave. The fourth octave would be what harmonic? It would actually be the 16th harmonic. So there's a little pattern here, 2, 4, 8, 16. The fifth octave would be the 32nd harmonic. So what you can do is you could do base 2 to the octave number would actually equal your harmonic number. 2 to the octave number will give you a harmonic number. So if I go 2 to the third octave, 2 to the third octave is 2 to the third is 8. So 2 to the third octave is your eighth harmonic. And this is a way you can use to figure out different notes. Okay? All right, so I'm going to kind of break out of this and go back to our page. And we'll scroll down here. So I have octaves, this doubling of the frequency, and 2 to the octave is the harmonic. So let's look at question 7.5 there. It says that the fundamental frequency is 20 hertz. The fundamental frequency is 20 hertz. What would be the frequency of the fifth octave? Okay, there's two ways to do this. Here's my 20 hertz is my fundamental. I want to go up to the fifth octave. Okay, so what I could do is I could just double every single time. That's one way of doing it, and that might be how some of you do it. So if I go up one octave, what would the note be? Well, I double 20, so that'd be 40. If I go up a second octave, that'd be 80. If I go up a third octave, that'd be 160. If I go up a fourth octave, that'd be 320. And I go a fifth octave, that'd be 640 hertz. So that's one way to do it. Just go ahead and double every octave, right? Double your note every octave. I get up to 640 hertz. But the other way to do it is to use this. So 2 to the fifth power. 2 to the fifth power is what? Well, it's 32. So 2 to the fifth octave would be the 32nd harmonic. Okay? So how do I find the actual note, though? Well, the 32nd harmonics are whole number multiples of the fundamental. So I would just take 20 times 32. The 32nd harmonic, 20 times 32 is 640 hertz. So you can do it either way. You can just double it 5 times and get your note. Or I could say, well, 2 to the fifth is 32, so I could take the 32 times the fundamental, and I'd actually know what my note is. Okay. So we have one little activity here. We're looking at a musical scale. A musical scale is, well, this is technically a physics music scale. There's a difference between a physics music scale and what all the music people try to do. So, because you have human voice, and human voice is a little bit different than instruments, but generally in band or in musical scale, we base it on a C, middle C, which is 256 hertz. 256 hertz. And we can get all of our notes by actually doing math on them. There's a mathematical factor to figure out all the notes. So a C is 256, and you'll notice all these math factors here are actually they're kind of fractions, right? So so you have one. Here's 1.5 right here. 1.5, right? 1.5. You have 1 1/3. 1.33, 1.25 is 1 1/4, right? You could do 1 divided by 8, so here's 1 1/8 right there. This is 1 2/3. If you do 7/8, you get, this is right here is 1 7/8, and then you have 2. So if you just take this factor times 256, any of these factors times 256, like if I take 256 times 1.5, 256 times 1.5 is 384. That's how you get all your other notes. All your other notes are completely mathematical. I know you think it's cool music, but music is math. That's why it starts with an M. Music is math. Okay, so if you vibrate your vocal cords at 256 times per second, you're singing a C. What if I double the vibration? Well, I go up to 512. I'd be singing a high C. See, that's 1 octave above, right? Okay, 1 octave above. By the way, this is not generally the scale you sing at. Any of you musical people might know if someone has ever tuned your voice to a little, a little frequency reader. It's based actually on a 440A. You'll notice A here is a 427. So 440A is sharp. Right? It's a little higher frequency than a 427A. By the way, what I meant by sharp is like that's a sharp symbol. That means a little higher than some other note. And then you have flat symbol. That means a little lower frequency than some kind of a note. Okay? All right. So anyway, what we want to do on this scale is I want you to fill out this entire chart here. So for like 2 whole octaves. So that's question 7.6. Continue to scale up 2 more octaves and to determine the notes up to the 8th harmonic. So if I start here with the C, there's different ways to do this. I mean, there's an easier way and there's probably a harder way. So I want to fill out this column all the way down to here. So how do I figure out what the D is? Well, I could take now my 512 note and take it times 1.125, right? I take the 512 times 1.25 and I have my new D note, right? And then I can take the 512 times 1.25 and I'd have my new E note and so on. But clearly, if you understand what's going on here, the easier way to do it would be if you got this C, how did you get this C? Well, it's 1 octave above, so you just doubled your 256 to get your 512. So that would be the easiest way. If I want to get this next C right in here, I'm just going to double the 512 and I get a 1024, right? And if I want to get this next C, I double the 1024 and I'd get a 2048. Some of you might have played this game, right? 2048. It's based on that kind of the musical scale, the bass 2 power, right? The bass 2 power. Okay, so and then if you want to get the D, you could just double 288 and get your D, and you could go ahead and do that. Okay, so then what I want you to do is figure out, what's the harmonics? What is the harmonics? So right here, clearly, we took 256 times 2. That's the second harmonic, right? It's the second harmonic. It's also the first octave. Right? The first octave. Okay? All right. If you doubled that again, you're right here. This is the and what harmonic would that one be? I'd like you to figure that out, right? So that would be the second octave, right? The second octave. Okay, so this would actually be the 4th harmonic. Then we're going to double again down here, and that would be the 3rd octave, right? 3rd octave. That would be the 8th harmonic. 256 times 8 should give you 2048. But you figure out all the other ones in between here, okay? And you'll figure out some other your other harmonics when you get down in here. Okay, so where down in here does the 3rd harmonic fall? And where down in here does the 5th harmonic, the 5th, down in here the 6th, down in here the 7th harmonic, where do they fall? Okay, and what you'll notice, if you're a musical person, you'll notice this. that you're going to get like a like your third, you're going to get like a G, okay, and you're going to get like an E, okay, for some of these. The seventh harmonic down here, you're going to get like a B, like a B flat, okay, because that goes well with it also. But if you play a C, an E, and a G, a C, a C, an E, and a G, okay, on the piano, that's a C major chord. It just sounds really, really good together. So when you get these harmonics of E's and G's, they're overtones playing with the C. That's a chord, what we call in music, and they sound really, really well together. That's why we call them harmonics. But I'd like you in your book to fill out the rest of this chart and figure out what note is the third harmonic, the fifth, the sixth, the seventh, and figure out what those are. And I think that's probably way too long of a video on just something as simple as harmonics and octaves, but I think that'll help you on the ELAB and on your Jedi trial.